Yeah, even though the number of infection, the increasing rate is a little bit not that fast compared to the 2 days ago. I think, well, we're still in a very urgent situation, so don't be too optimistic about the about the dissemination of the COVID-19, especially in this week. I think we still have wait and see how it evolves in the following week. So, okay, so nice to have you back here. Okay, so we need to finish the chapter 4 today, then move to the next one. Okay, then. Okay, so look at the 4.2.3. This is right here, textbook. Yeah, let me just shrink the screen a little bit. Hold on. So we just finished the cross validate, the cross correlation pre-widening last time, Monday. Identification, then we have mentioned this, the offline estimation of the transfer function model. So we mentioned this already. Yeah, the semiconductor manufacturer. Oh, okay, let me review this. Yeah, this is quite typical semiconductor process called CMP, which was invented IBM in 1980. So called the chemical mechanical polishing CMP. It's an important processing step in the manufacture of semiconductors. The primary goal of the process is try to polish the surface of the wafer, essentially make the silicon wafer flat, remove the some extra nitride or the most of it should be the nitride. In CMP machine, wafer pressed down by the handler onto the rotating table or platen that has a polish pad has been equipped in the above. A slurry, in the meantime, slurry is added to the pad. It's like a really a sticky liquid has been dropped to increase abrasion. So planarizing the wafers is of critical essence to be able to add more circle to the surface of wafer. So the two goals of this process are in the following. We have two folds. First one is a non-uniformity of the wafer. So actually, the process engineering going to measure like 15 to 20 measurement. The position will be all over the surface of the wafer. So it is a measure of the variability of the thickness of the wafer. Then the process engineer going to compute the standard deviation of those thickness of the wafer. And we expect the standard deviation as minimal as possible. That means this is the flatter of the surface of the wafer is. And the removal rate of the silicon oxide, so it could be nitride or oxide. So some of the controllable factors are the downforce pressure, the spin, or the handler, rotating speed. Yeah, let me let me show you some picture to give you some idea what is the CMP is. Yeah, CMP. No, I like to have an English version. Yes, like this. So this is this is spindle. So this is a polish pad. So the wafer going to be attached on the back of the spindle. So the table and spindle going to rotate on the same direction. So in the meantime, so we also equipped with a polish slurry, like a really sticky liquid on the surface of wafer, and also have a conditioner. This is try to fine tune the abrasiveness of the surface of the wafer. No, the abrasiveness of the surface of the table. So so this is the basic schematic profile CMP process in action, or something like that. So you can type in the CMP to get some detail. Yeah, there's some detail. So if you like to have, yeah, let me CMP. Let me give you the, yeah, this is some basic description about the CMP. Okay, let me just leave the link in right here. Hold on. The CMP for your references. Okay, then some of the controllable factor are the downforce pressure, rotating speed of the platen, amount of slurry that is sticky, really sticky liquid, and the polishing time. So in experiment, let us consider removal rate in angstrom per minute. So angstrom typically this is a unit in computing the critical dimension in semiconductor manufacturing. Let call the yeah Armstrong, and so typically this is 1 times the 10 raised to power the minus 10. Okay, call the Armstrong. Okay. So so in Armstrong per minute to be the quality characteristic of interest to the process engineer, and the platen speed to be controllable factor in RPM. This is revolution per minute. Then removal rate is response that manufacturers wish to maximize, since we like to remove as many as possible, since after lead time is money. So we're going to fix the polishing time typically. So gonna keep the polishing time fixed all the time. So so that is a measure of how fast the job can be done. Then to identify the input-output transfer function, all other controllable factors were fixed at the nominal values. So the platen speed was varied. So change the platen speed from time to time, very rarely every 10 wafer within the interval. Then the input-output data of this example can be found. So yeah, since we don't have any homework for this chapter, so we don't provide this data file to all of you. And time series data applied in the figure 4.6 like this. Yeah, the A is a removal rate like this, B the platen speed. So every 10 wafer is going to just change the platen speed like this. So back to here. So computation will perform in both access or Minitab system ID toolbox. So the control toolbox is quite popular in electrical engineering and control engineering. So yeah, you can see that the first step is to pre-whiten the input series. Figure 4.7 shows the autocorrelation part of autocorrelation. Figure 4.7. Yeah, like this. Yeah, this is a sine wave. No, this is not sine wave. Exponential decreasing. So and then A is a sample autocorrelation function. B is the partial autocorrelation function of the Platon speed. Example, you can see the cutoff. This is the tails off, right? So show the autocorrelation and the partial autocorrelation function of the controllable factor. Since yeah, so you can see that since the Platon speed was vary only a few times over the 100 observation, so it's a mean wander from time to time. So it changes from time to time. So it is non-stationary, as can be seen from the plots. So what does it say? And this is so the B, the Platon speed is non-stationary, right? Up and down, they don't have the fixed mean. So so non-stationarity behavior, we made the estimation cross-correlation very difficult. So like this, yeah, it's important. This non-stationary, I'm sorry, this one, okay. The non-stationary behavior will make this estimation cross-correlation very difficult. So we need to do some pre-processing of the data. So removal rate. So yeah, in this case, simple first order difference is good enough as a pre-whitening filter. So in this case, a simple first order difference will be applied. So the removal rate series was also difference one time. Figure 4.8 show the impulse response function. 4.8. Yeah, let me see, 4.7, this is 4.8. Estimate impulse response function between the difference Platon speed and the difference removal rate. Okay, so this is estimate impulse function. Yeah, like this. This is pretty much of the same style and the same pattern. It's quite similar pattern we mentioned in the definition of the transfer function. Right. So in this case, the graph indicates CMP is simply pure unit delay process. So that is a no process dynamic and delay is only one-time unit. Look at this one. I'm sorry. Look at this one. So this is called a pure unit delay process, since this is Debye control with respect to the difference data. So this is Debye control process. Okay, then, okay, let me, so that is a no process dynamic. This is only system disturbances. Here, the time unit is simply the run or batch or number. So typical run could be a one wafer, could be a batch of wafer, or a couple of batches of wafer. So the dynamic behavior of this process comes from the dynamic behavior that belong to the wearing off that occur in the polish path. So it could be come from the wearing of the polishing path. Yeah. So typically we see the process ages. something like that. It could be process age or tool wears. So, so which can be modeled by a non-stationary disturbance like this. This is different data. So xt, t minus 1, this is debit control. So this nt is disturbance. The nt is disturbance model, anti-disturbance model. And in here, xt is, excuse me, xt is this controllable factor in transfer function model. Okay, then this, yeah, let me see that. The binom is the initial weight of the transfer function related to the controllable factor, binom. This is a B, I'm sorry, the B, the initial weight of the A, yeah, let me see, how can I call that, hold on. Transfer function, let me, the B polynomial, okay, this is B polynomial. The weight of the B polynomial of the Back-Cauchy operator, yeah, something like that. So binom is the initial weight of the polynomial of a B polynomial in terms of the Back-Cauchy operator. Okay, I think you have a basic understanding how transfer function can be built. Okay, I'm gonna skip that. Finally, yeah. Okay, then, okay, let me describe a little bit. So let me see the subplot of A and B in the figure 4.9. So autocorrelation function and partial autocorrelation function of the residual of the prelim model with different data. Since why with different data? Since you can look at that. Since it's a non-stationary, we like to do the pre-widening of the input variable. So this is output variable. So we do both to do the pre-widening to turn this two series into the alpha t, like we mentioned on Monday. Let me say that. What is it? Alpha? No, not here. Not here. Pre-widening. Yeah, let me see that. Yes, right here. Okay, then A of C. So do the pre-widening, transform xt into alpha t. Yeah, this is called the pre-widening. Then after we widening, yeah, this is quite nice. So partial called residual of this one of example 4.3. Okay, so based upon the different data, the model can be constructed like, I'm sorry, like this. So this can be built, right? So okay, let me say that. So based upon this, I'm sorry, based upon this model, fitting the model, then okay, then to be the difference input and output gives the estimate of this one, the initial weight. So the sample autocorrelation and partial sample autocorrelation function of the residual obtained from this. This is a deviation from target. No, this is a forecast error. So which can be transformed into the YT hat equal, since we different the data, since the binom is a 32.15, so different the data xt minus 1 is shown in figure 4.9. Yes, 4.9, 4.9. Yeah, like this. Yeah. So we also like to add the disturbance like this. This is the tool wearing. Since the model has been fitted based upon this. So the sample autocorrelation function clearly cuts off after, let me say that, after lag 1, right? Cuts off, why? Cuts off at lag 1, right here. Cuts off after lag 1. So it is quite obviously them. So while the first 2 legs of the sample partial, let me see that. The sample autocorrelation cuts off after leg 1. The first 2 legs of the sample partial autocorrelation are significant, so they indicate a tentative disturbance or MA process. So yeah, this is like this. This is a cutoff, I'm sorry, and then this is like exponentially decreasing. So based upon this type of observation, so this indicates a tentative disturbance MA1. So we add the NT at the MA. So this is MA1. Okay. So this previous to is a transfer function for sure. Then add a disturbance. Then we are done. So to the data, we obtain the B-known, we have this, so re-estimate the parameters. Since originally we have this one, so this is before we add the disturbance. Now we added the disturbance into account, then we have a re-estimate of the initial weight and say that the 0.7 something, so both has been highly significant. So at this point, the model is ready. So this is YT, different data. Yeah, excuse me. So this is weight, yeah. Then this is IMA. So epsilon, so we fit the residual. This is close to the Y sequence. So the fluctuation is a standard deviation of fluctuation about 30.19. So which corresponding to the per unit delay or responsive process called the IMA. So this is transfer function B equal to R, S equal to 1. Then this corresponding to the IMA difference 1 time. So we difference 1 time. So which corresponding to IMA, integrated moving average 1 disturbance. Yeah, like this in here. This is IMA disturbances. So I think, yeah, this is a good illustration how the transfer function could be built in order to characterize the semiconductor processes. Since we cannot go to the class, so now let's try to explain the table. Made me difficult to do the presentation of how those models can be fitted. So now we move to the section 4.2.3. So we're going to switch. We're going to switch to the slide. So is any questions so far? I know this is difficult. Yeah, this is really difficult. So especially in the online class. Okay, then. So let's do the let me that should be 4.3, I believe. 2.3 other input output dynamic. Yeah, like this. Okay, I understand it's quite difficult for you since this is the first time you ever you don't have a previous exposure to the control engineering practice. So it is quite difficult if you in the future you really want to get into the semiconductor as your career. So this course, the material I cover in this course is important to you if you like to work in TSMC, UMC, or something like that, or Vanguard. You like to work in for the power chip or like micronics or something. So yeah, I know the control engineering is not your backyard. However, you need to try to learn yourself. So I strongly suggest you read the book. So you need to read the book several times, over and over and over again. So to make yourself feel comfortable about the content of the textbook and the material covered in the class. Any questions so far? No? John, any question?
No.
No. Somehow, any question? Hello? Somehow?
No.
Okay, so let's move on. And the other input-output dynamic models, the Fox and Jenkins transfer function has an advantage that why we say that it avoids the common term that might have additional complexity. So like this YT B over A transfer function C over D. So the B over A transfer function for the X, the come into that, the B is delay, into the sigma, it's a summation, sigma. Summation, is it called a summation? Then, so entry is disturbances, so the summation right here. This is not ET, the epsilon T. Epsilon T is the arrow. So this is the arrow term, okay. Then coming to the this is not transfer function. This is polynomial C over D to produce disturbances. Then add them, so they are combined to generate the YT. YT the observable. There's a you can say that this is observable value, or they called the metrology data. Okay, call the metrology. This is YT. Metrology data. Somebody refer is a measurement and measure. Sorry, I need to turn off my line. I'm sorry. Hold on. Give me a minute. Okay, then other input-output dynamic system in econometrics. Econometrics is a popular model called the RMAX. The AR is autocorrelation. Where's the AR? Right here. The MA, the moving average, X is called the exogenous X into the B over F into this one, C over F into this one. So we have a called this exogenous called the RMAX. Typically, yeah, let me see. Do we have no? No, it doesn't have a no. No. Okay, it doesn't come with illustration. I'm sorry. Yeah. No. Yes, if have time, I'm going to go back to the table in the chapter 4. So if time is allowed, I think, yeah, this is important as well. For I am the additive. Okay. This is the transfer function. Hold on. I try to find that diagnostic check-in 4.2. Okay, back to here. However, so this is called exogenous. Typically, is used in like a stock market of the Taipei, a stock market of the New York. Exogenous, the XT typically this is the factor, political factor. So other process dynamic model, input-output dynamic model. So like this, the first one, this divide by B, divide by F. The YT could be B over F, XT minus B, the C over F, the transfer. This is disturbance model. If noise is turned is instead an AR, so this is F, B, and then this AR, the 1 over D for sure. Okay, there's no C. If the noise model follows an R model, so this is going to be the C over D core. If this is general single output and single a single input, single output, we like to call it a seesaw. So a single output F B over A, C over D. C over D is called a seesaw process. Then we go to the 4.3 diagnostic checking in the transfer function. So denote the residual of the fitted model by this. Typically, always use the residual for diagnostic checking. This residual equal to the observed value minus subtract the fitted value. Suppose the true system is this one. So but with fitted model, this one, so YT minus YT hat going to be the forecast error, or called the residual. Hold on, let me type in the residual. Yeah, I also type the Mandarin. Okay, in Mandarin call it 残差. Okay, 残差 that means the difference. So the residual 残差, which is considered no, the scalar. Scalar, which is not a random variable. Actually, no. Then so if okay, then we like to have a rules. We have a rules. If there's a no system model mismatch, no system model, then so let me just make some adjustment. Okay, it doesn't show the way I want to. Yeah. So this epsilon T will not be autocorrelate nor cross-correlate with the input. So that means you did this cross-correlation. Let me show you. This is cross-correlation, two series XT and YT, input and output. Yeah, it's no model mismatch. That means we choose the model correctly. Then there's a no system model mismatch. So if mismatch occurs, then this is not zero. So epsilon T and epsilon T So this two going to be autocorrelated, and then so we're going to show you the picture. So third one, if the transfer function is correct, no mismatch, but the noise model is incorrect, then the epsilon. So this is after pre-widening, the noise must be autocorrelated but not cross-correlated with the xt, the input variable. So remember, very important, transfer function is correct. We choose the right transfer function, but noise model is not right. Then this one, residual going to be autocorrelated but not cross-correlated. Okay, then this is the rule number 3. Rule number 4, if this is R, the cross correlation shows structure. No, the R is this is sample autocorrelation function shows structure, but the cross sample autocorrelation function does not. The noise model is wrong. We need to choose the so we need to fit the residual once again to find the better one. Okay, so this is kind of complicated. So these are 4 different rules. So if the transfer function is incorrect, even if the noise model is correct, okay, then this is the model, and then so epsilon. So the residual autocorrelation and the cross correlated with the alpha. So both the partial autocorrelation function and the sample autocorrelation function shows both autocorrelation functions show structure. So this is rule number 4. This is rule number 5. So overall test for the lack of structure in the first K autocorrelation of the residual is given by this. Yeah, let me show you this. Yeah, this is some. Like that. Hold on. Like, yeah, there's a several point I mentioned. 1, 2, 3. Yeah, then 4. So an overall check for lack of structure in the first K autocorrelation of the residual is given by this one. Okay, by this one. So where n is the total observation minus the maxima of the R S plus K minus P. P is the number of the parameter in the model. So this statistic is testing well, null hypothesis, the rho equal to 0 for J follow a chi-square distribution. So distribution evidently rejection region is the right tail of the distribution, since the chi-square distribution is the one-sided. The chi-square right here, the chi-square distribution is one-sided, and since the large value will be due to very large autocorrelation, so going to reject the null hypothesis. So typically we wish, if the model is correct, then we wish the chi-square test statistic will be very small. In such a case, then we do not reject the null hypothesis. We accept the model which is considered adequate for the data. Similarly, an overall check the null hypothesis of the cross autocorrelation. So in here, this is the autocorrelation, and this is the cross autocorrelation. To compute, so we have Q1 and Q2. Q1 is for the autocorrelation, Q2 for the cross autocorrelation. So you also follow the chi-square distribution. So let me see that. Do we have no? Do you have an example? No, it doesn't show. Okay, let me see that. If I can find that, no. Okay, yeah, we only have this example, 4.10. A is a sample autocorrelation function residual, this is REE, residual to residual, A. Okay, this is upper bound, lower bound. The B, the sample cross autocorrelation, the filter alpha T and beta T, cross autocorrelation. Yeah. Then we have example. Let me see that. Do we have a data? Okay. Then, yeah, let me go back to here to have a. Okay, then we give you recapitulation. Okay. This is kind of messy. This is diagnostic check for transfer function. We'll do the recap. Okay, do it one more time. Then YTO rate. This is R. This is the S, and this is the B, RSB. This is the order of the transfer function model. So we'll do the diagnostic checks in order to check the appropriateness of the model. So if the sample autocorrelation shows structure, the the sample cross autocorrelation doesn't show, North model is not right. Then second, if the sample autocorrelation function shows structure, the sample cross autocorrelation function shows structure, both show structure, then we're going back to the root cause transfer function is not correct. We need to consider, well, yeah, how can we choose the right one? Yeah, this cannot be right. Might be the B, maybe the important X is not included. So we need to reconsider. So how can we improve the quality of the transfer function? So this is SAS. This SAS thing. So we don't use SAS, so going to skip that. So before we jump into here, we'd like to read this example. Okay, we'd like to read this example. We show that we give you 1 minute. No, we'll give you 3 minutes for reading this. We're going back after reading the example 4.4 in 3 minutes. Please, everybody do it now. Okay, so I give you 3 minutes. So, okay, we are back. So example 4.4, this is diagnostic checking for the semiconductor manufacturing process. In the previous example, we mentioned in the CMP process example 4.3, the tentative model fitted was the, okay, Nabra YT equal 33.86, Nabra XT minus 1 in here. So it is RSB B equal to 1. This is IMA, 1 minus 0.7061, the epsilon T. So figure 4.10 shows the plot of sample autocorrelation of the structure, sample autocorrelation function of the residual. So this is REE versus K, the first one, this one. And the plot of the estimate cross correlation between the pre-whitened input and the residual. So it's a plot of the R alpha EK versus K. The cross correlation alpha is the input, E is respect to the output, a residual of the output is alpha E. So in both cases, no significant correlation can be seen, indicating both the transfer function and the disturbance has been identified correctly, since none of them going to extrapolate the upper bound and lower bound. So yeah, we so lucky. We are so lucky. We find, okay, right here, we find this, not here, not here, this, no. Let me do this right here. This. Yeah, we are lucky to have this one since we estimate. Yeah, the model is quite provide a fit to the data based upon the observation of the REE and R alpha E. Based upon the observation of these two plots. So then overall check for lack of correlation can be performed. The Q1 and Q2 statistic referred earlier using the SAS statistical analysis system. We found Q1 sets 19.7 up to K24. A p-value, where is that? The p-value, okay, the Q1 19.67 up to K24, up 24. This is around there. So the p-value is quite large, so this is not rejecting null hypothesis. There's no evidence to reject the null hypothesis with a residual are uncorrelated. Q2 the 18.84 up to 23. P-value is quite big as well, this which indicate that there's no evidence to conclude there's a significant cross correlation lab between the input and input alpha t and residual. This is ET with respect to the output. So based upon the statistic and the graphs we show, we can conclude that the removal rate model is quite fit to the data we have. Okay, so we're going to skip the SAS right here. Okay, so we're going to, let me see that, do we have this? Okay, we're going to discuss this. We're going to discuss this example 4.6. So this is close to 10 o'clock, so we're going to have a 10 minutes break. Please be back after 10 minutes break. I see you later. Okay, we are back. We are back to the classroom. Let me see. Okay. Can you hear me clearly? Can you hear me clearly?
Yes.
Okay, thank you. So let's go back to the here. Okay. Okay, the example 4.6. This is transfer function of not example. So it won't matter we use SAS or not. So you can use a MATLAB or other. Or there's a scikit-learn package also available. So consider a continuous polymerization process in which it is of interest to model the polymer viscosity as a function of changes in the reactor temperature. So viscosity is going to be Y and Xt going to be the temperature. Let the YT be the mole index, a measure of the polymer viscosity. Let ST, input variable or controllable factor, be the average temp of the reactor. Samples are going to be taken every 2 hours, once per 2 hours. So X denotes the average temp over a 2-hour period. So the file polymer.txt contain the input-output time series data, which was plotted in the figure 4.11 right here. A is X should be the input, XT. Y, B should be the, no. A should be the Y. The B is the temperature control variable, XT going to be the input. Then the first step, we'd like to build a model for the input. So from the sample autocorrelation function of the input, it is evident that the input need to be difference one time. Then XT and XT is right here. Okay. So it's non-stationary, so going to difference one time. Then so not here, I'm sorry. Where is that? Oh, okay, right here. So first order difference transform the input into a white noise sequence as seen in the autocorrelation plot for the difference input. So force us to treat a simple difference as a pre-whitening filter. We estimate model with the statement. Okay, so go to yes.
没有画面。
Okay, I'm sorry. 抱歉。对不起，我忘记了。对不起。Yeah， 抱歉。看得到了吧？
看得到了。
Okay, I'm sorry. My mistake. I'm sorry. Yeah, so like this is AT, BT. So this is let me say it again. AT is male index. This is output. This is input. So different data one time. It is a non-stationary. Okay. Non-stationary. Then finally. So okay, then next we want to estimate the cross correlation between the pre-whitened input and output. We wish that any further modeling be made on the YT and XT. This is a number of YT and XT, like this, figure 4.12. Yeah, this is sample cross autocorrelation and the prelim parameter estimate by using the SAS. So let me see that. Okay, this is cross correlation. This This is alpha between the alpha t and the beta t. And yeah, this is the parameter estimate. This is the estimate. This is the two parameter in here. Okay, then. So from here, the cross correlation function shown in the figure 4.12. It is clear that this is a numerator. This is numerator. This is in the upper part of the fraction dynamic process with two significant lag delay equal to the 1. So this K RSB. This is 1. The K equal to 1. So two significant. So in here. In here. So when we difference 1, this is a 1 and 2. The 2 lag. Let me see that cross correlation 0, 1, and 2 right here, right? This is 2 significant. I'm sorry. The 2 significant lag right here. Okay, then. So, so input statement specified above generate the prelim parameter. So to build a disturbance model, the sample autocorrelation, sample partial autocorrelation of the residual of the prelim model are needed. So they are plotted and shown in figure 4.13. 4.13. Okay, if this is true, okay, so this is a 1, 2, a different time, and we see that partial autocorrelation one. So you can see that, yeah, this is the autocorrelation function. This is a partial autocorrelation. We can see that this is 1, right? Here is significant. This is a cutoff, and this is tails off. So it gotta be an MA process. So cool. So this is quite straightforward in terms of the knowledge we obtain from chapter 3. So this is MA1. So clear. Let me just right here. Okay, as can be seen from the computed estimate autocorrelation and the partial autocorrelation function, yeah, it's an MA1 for sure, right? Since the sample autocorrelation function cuts off after lag 1, the partial sample autocorrelation function tails off. It's so clear. It must be an MA1. So we just MA1 right here. Difference. This is the 2. Okay, like that. Yeah, this is MA1. The MA1, right? Then we just extended. We just extended Y over B. So the Nabra YT equal to this 0.1866 xt minus 1, 0.23012 x minus 2 right here. And the Nabra, the cancel out, and divide by the Nabra is 1 minus backwash operator. So this, I'm sorry, this has been parameterized into the 1 minus 1 minus 0.46438 backwash operator epsilon t divided by the Nabra. Nabra is the 1 minus backwash operator. So this is our model. So cool. So cool. Yeah. Then look at that. Furthermore, we'd like to check the Q1, Q2. Hold on. Then further, we have this one, we have this one, we have this one. Hold on. Okay. Then epsilon. Hold on. The statement. I need to continue the statement. What is the statement? Model is this one or then yes, we have it. We have it with The sigma epsilon 0.0037. So this is the error. This is error variance. So let me 0.037. Where is the 0.037? Standard deviation. Gotta be somewhere. We try to find that. Sigma, not here. Not here for the p-value. Yeah, it's a quite. This is, look at those Q1 and Q2. Look at that. The p is quite big. This is do not reject the null in here. Would like to see the p right here. So we do not reject the null hypothesis since the p-value is so big. And also we like to see the variance. Yeah, right here. The error variance 0.00372, right here. This is 0.00372. Know that the error term is IMA. Where's IMA? Right here. IMA corresponding to right here. This is IMA. Since the nabla has been divided, so move to the right hand side. So this is IMA. Then further, okay, going further, the sample autocorrelation function and the partial autocorrelation function of residual do not indicate any remaining autocorrelation. The Q2 statistic up to the leg 23 is 1624. Let me 1624. 1624. Where is the 1624? Q1. Let me see that. Hold on. Leg 23, 1624. Yeah, 16. Yeah, this is degree 23. Hold on, I need to find that. Let me see that. Q2. Q2. Would you check the textbook? Let me find that number. Yeah, right here. 23 should be the 15.72. Correlation check residual with the input variable. The cross correlation should be this 15.72. Yes, it's right here. This is a partial correlation. Yes, right here. 15.72. 15.72. Oh, no. Should be, hold on. Parameter, oh, this is final. Final parameter estimate diagnosis. This is Q2 right here. I'm sorry, my mistake. Q2 right here should be this. Okay. The p-value is so big, and up to the leg 23, 16.54. This is 16. Yeah, I know. This is 1624. How come? Am I get something wrong? Sample autocorrelation partial residual. Sample of the partial sample do not indicate. Yeah, it should be this. Q2 indicating this is cost. This is correlation of residual input. Let me see that. Yeah, I think should be 16. Gotta be typo. Should be 16.54. Okay. So corresponding p-value overall is no significant 0.778883. 7883. So this is a typo. 1654. This should be the 1654. This is typo. Please correct this. This is not right. Should be 1654. Okay, then, so there's no evidence to reject, so conclude the model is adequate. Okay. Yeah, I know this is quite complicated. Okay. Then we have introduced two examples. Then we like to move to the 4.5 offline some idea. So we don't use this to let me see that. Okay, let's go back to the slide. Let's go back to the slide. So the internal and external dynamic model, the entire dynamic model we have seen is from an external viewpoint. So we treat the process as a black box. Internal process is treated as a BLACK black box. So the model characterizes the input-output relationships. And the internal model, on the contrary, describe all the internal coupling among the system variable. Actually, yeah, internal modeling refer typically the internal modeling refers to the modeling by WE, the chemical engineering or electrical engineering or mechanical engineering. So internal modeling refers to the modeling by using electrical engineering, chemical engineering, and the mechanical engineering. So usually knowledge about the physics or chemistry is necessary if the system is described as set of the differential equation. Actually, we don't do that. For IE, we are industrial engineers. So this equation lead to the so-called the state space representation of the system. So actually, try to cover that. No, in my last 10 years teaching of this class, don't have time to cover that. The state of the system, a set of the number, the state variables, such as the knowledge of this number, the inputs, the equation describing the system. You can forecast the future behavior of the system. So actually we do define what is the state variable before we model the data. So we construct the model by using the data in terms of the data. So the state variable is internal variables that determine the future behavioral system given the input and the current state. So what is the next step? So what is the next state given the current input? Okay, this they're going to be the end of the chapter 4. So move to the next one. Hold on, let me go back here. I switch to chapter, the next one. Yeah, let me. Okay. So we're going to switch to the chapter 5. Optimal controller. Okay, did I send you the slide already? Do you have it? Using this. So do you have the slide of chapter 5 already? Do you? Yes or no? Hello?
Yes.
Okay, so now we proceed to chapter 5. Is chapter 5 going to be yeah, self-tuning, yeah. Okay. You'll be covered. It get covers in the as a project number 2, the final project. The final project is a little bit harder. So the final project going to be individual as well. Final project will be in basis. Final project will be individual basis for sure. Everybody should do your own work. Should be implemented in MATLAB or C++ or Python. So you can choose one. You can use the Python or the C++ or the MATLAB. I think the Visual Basics is still is acceptable. Visual Basic VB. So I strongly suggest you to start as early as possible. So it's going to take you at least 2 to 3. Now, if you understand that, it's going to finish in 1 week. If you typically do not review on a weekly basis, it's going to need a longer time. Okay, so I just remind you, you need to start your project number 2 as early as possible. Then time series analysis optimal controller. Let me move to the chapter 5. Okay, optimal feedback controller. It is this going to be the most popular in TSMC. They use it throughout the fab. So, well, this is important, very important class, very important chapter. And okay, so let's get started. And so there's a textbook in the textbook. You can go to a library or go to the web to find this is this guy who is an European, and he wrote a very classic textbook, Introduction to Stochastic Contour Theory, Astrom. It should be Leon Astrom. This is a minimum variance controller. The paper can be referred to the 1992 Technometrics. So this is the first one, process dynamics. Process dynamic though. So it is assumed that the process is simple, so linearly. This is a linear dynamic system with one input variable and one output variable. So the input and output relationship can be given by this. Okay, this is the AR. The B non T minus K, B1 T minus K minus 1. The top. So this is system dynamic, T minus K, system dynamic. So the K is a system delay, time delay. using the backwash operator. So this part on the left-hand side and represent as an 8-polynomial times yt. And this part transfer function, this is the B1 backwash operator in terms of backwash operator and t minus k. Or if A is stable, stationary, it can move to the right-hand side, yt equal to the B over A times the t minus k. K is the system delay. So the environment refers the process disturbance. So let me just remind you, the K is the system dynamics. Okay, this is the system dynamics. How far of the xt going to have an effect on the output of the yt? So it's called the system dynamics. Instead, the environment is referred to noise dynamics, or called the disturbance system or process disturbances. The process disturbances is NT right here. Okay. So since it assumes the system is linear, so we can apply the principle of the supervision. The principle of the supervision. Let me show. Yeah, the principle of the supervision, that means okay, so this is the additivity. The principle of additivity. Okay. Then assuming the disturbance is Gaussian, so Gaussian is a normally distribution, so we can represent that the NT on the top, the numerator is referred to the moving average, and the denominator is referred to the autoregressive. So C1 and A2 are polynomials, and the epsilon t follow the Y sequences. Okay. So the minimum variance controller right here. So the feedback controller also feedback principle, actually Y is defined as T minus Q. Target from the set point or target. Q is a quality characteristic. If the Y greater than 1, we increase X. If the Y is smaller than 0, that means the target. No, the target smaller than the set point. Then we decrease the axes. So the X move in the opposite direction or negative direction than Q. So sometimes this minus sign is included in the control equation like this. Okay, so YT is defined as the difference between the Q and T. This is set point, Q right here. Q is a quality characteristic, and subtract the target is greater than 0 or less than 0. So the resulting block diagram is neatest. See the figure like this. So this is a controller. The previous controller. So this is the X called the process plant. P-L-A-N-T, plant. I'm sorry, not this one. So this is a plant. So producing the quality characteristic y, and the Q minus target is right here. The Q minus target to producing the YT. This is output minus target. It is a deviation, so we multiply -1 into that. So Y into the controller XT into the controller. So you can see that since if Y greater than 0, no, Y greater than QT, no. Okay, we put a negative of that. Okay, in this case, we should manipulate the XT in order to get the QT output close to the target as possible. So right here. So the information going to feedback into the controller and to control the XT in order to make the plan to produce the output as close to the target as possible. So put the process right here, put the process right here, process multiplied times a target, and the Q put multiply the multiply by -1 to Q. So that's a T minus Q, the information provided into the controller mechanism or controller block, and produce the X is provided to the plan in order to generate the Q as close to the target as possible. So this is a block diagram in here. So this is block diagram. The block diagram. Okay. So in this case, or the second form of the negative, in terms of negative, this one, put the negative, this. So we put filter like this, so negative feedback. So this is the negative feedback principle. Based upon this principle, the block diagram can be represented. So the controller, this is a Q as well, and target is a Q minus T right here. So put a negative here. So use negative. So actually, this is the negative feedback principle in here. This is YT minus Q divided deviation T minus Q. In here, the T minus Q, and put the F, the sec. So just use the Q minus T as well into that, and the controller would put a negative on that once a while, and the feedback into the process. So you can choose either one. So they are the same. They are totally the same. Totally the same. The third equivalent negative feedback controller for a constant target. So likewise, so we just directly define y equal to the q minus t and feed back to that and into the minus f, and then produce the xt, the xt to the process. So actually they are the same. They are the same. The minus f is right here. Okay, this is minus f. So x move in the opposite direction from q, the quality characteristic. So that means if the y is greater than 0, so t is greater than target greater than 0, so increase x. So if the see that if the y is less than 0, is the target less than quality characteristic, so we decrease x. So quality characteristic is bigger, so we decrease x. So we need to put a minus right here. So call the negative direction. So x, like this. So x gotta be moved. X move in the opposite direction of the Q. It depends on Q. If the Q is small, we increase X. If the Q is big, then we decrease X. So in the opposite direction. So that's why we put the negative right here. Okay. I'm sorry. This is negative. So we have 3 different forms. Okay. Is there any question so far? Oh. Okay, the negative feedback principle. Okay, then, so the system and the environment are characterized the block diagram. Okay, in here. So this is summation, and the epsilon t come into the polynomial. So we have a AR, 2AR, AR for the AR A1 corresponding to YT, A2 corresponding to the disturbance. So C1 over A2, the arrow come into the C1 over A2 to produce the NT, and XT minus K. So T minus K into the system minus K. This is K. Backwash operator into that. And the B1 over A1 to produce Y. So YT plus the N, no, I'm sorry, signal plus the disturbance together to produce YT. So this is the signal. So the signal plus disturbance equate to the output. Then this is YT. This is the true. This is the true response. Hold on. So YT is the true response value. How can we know? So it got to be measured via metrology tool. Gotta be MEASURE, measure. Gotta be measured by a metrology tool. So in here, so we also there's some error incurs during the metrology called the metrology error. So metrology data. That's why we have discussed the gauge GUAGE gauge measurement system, gauge measurement analysis. Okay, the gauge measurement analysis. So this is the gauge GUAGE, the variances equal to the repeatability plus reproducibility. Okay, the gauge. This is R-nar analysis. Hold on. RNR analysis. Then the repeatability refer to the gauge UAG. So repeatability refers to the gauge, and the reproducibility refers to the operator. Okay. So this is QC. So next page, the minimum variance control, we can simplify the model by making the multiply A1, A2 on both sides. So the A1, A2 YT, B1, A2 XT minus K, this the system delay. So this is a process dynamic. Then C1, A1 epsilon T. So A1 times A2 to produce A, B1 times A2 to produce B, C1 times A1 to produce C. So collectively, we have A YT equal to the B XT minus K plus C epsilon T. So we're back to the generic form again. So then also we'd like to talk about the admissible control laws. Let me see the what is admissible? Describe part, no. Hold on. No, don't have it. Okay. Okay, back to the side. Admissible control laws. XT is admissible if it is a function. So I'd like to calculate XT. So the typical question to be asked: what is the XT to be chosen? Always like that. How can we choose? How can we choose XT? Then we might well say, okay, we'd like to choose XT. CHOO, choose XT to let the YT close to target. It could be, yeah, try to, or we choose XT to have a minimum variance of the output YT. It could be, or we like to choose XT so that the YT remain within a reasonable range. Yeah, it could be, right? Anything else, ladies and gentlemen? What else? What can we do? Hey, Jen, what do you think? Hey, Jen,
我在
Do you know the question? Typically, we choose XT. How can we choose ST? Yeah, you can speak Mandarin. I don't care. Just say something. 你们可以看到我打字吗？
可以。
Okay, so what is your idea? What is your idea? Anything? Yeah, don't worry about that. You just speak up. Don't worry. Say as what you want to say. 上豪 what do you think? 上豪 Hi, what do you think? Yeah, anything. At least you need to say something. Or John, you would like to help them? John, what do you think?
老师我在。
你就随便讲啊。What do you think? 哎，你们3个都在学校吗？还是在家里？
在实验室。
在哪里？
实验室。
哦，你们不怕死啊？你们还跑到实验室去？
我们今天
啊什么？
东西。
什么？
来拿东西。
Okay, sure. And about that, what do you think? Or yeah, we can choose XT to have a limited. Choose XT within a limited range due to technical limitation. Yeah. Okay, we stop here. We have a 10 minutes break. Okay, we're back to work. Okay, we're back to work, back to the minimum variance controller. So Jin, is everything doing okay? Jin,
Yes.
I mean daily life, I mean.
Yeah, it's okay.
How can you get the mail?
I buy it in canteen.
Okay,
Yeah, it's open.
it's open, the cafeteria?
Yeah, but
Okay.
we can only take away.
Okay, sure. Yeah, it's better. You take away back to the lab.
No, I mean in dormitory.
Okay, dormitory. Okay, back to dorm. Okay. And you, so you stay at home or you stay in school?
I stay at home
Okay, cool. So where is your home?
next to school.
Not to school, actually. Okay, so this is a rented apartment, right?
No.
No, this is your house?
Yes.
Okay, cool. Okay. So, okay, I think I hope everybody just stay away from trouble since I just got a message, the National Taiwan Hospital, the biggest one, the highest level in Taiwan. So within hospital, they now have internal infection. Over 10, I think we have 10 internal infection cases. So I think the thing will get severe, will become the getting worse from day to day. Even though we look the number of the cases of infection decline, however, it doesn't say anything. Things are always this a lagging indicator. Since the number we reported is a cases already happened 2 weeks ago, so it's a lagging indicator. Do you understand? So we only report something already happened for a while. So it is so going to deal. So all the infection developing in community, yeah, quickly. So so we don't have the capability to do the screening since the PCR, the capability of the PCR in Taiwan is limited. Yeah, so that's why we don't. Actually we don't. We have no idea how many real infection cases in community as compared to mainland China. They just do the almost 100 inspection by PCR. So in mainland China, they know where is the real infection area. So they block that area. In Taipei City, even though in Wanhua, in Banqiao, in somewhere, we know they are hot area of infection. Now, is that really only the hot spot of infection? Actually, we don't know yet. We don't know yet. You got to be some places else. We don't know since we don't have a capability to do the screening. So this is the problem. Okay, back to work. So hope everything is doing fine. Okay. So there's another things as compared to me. For you guys, since you are youngsters, your age between 20 and 25. Of your age, you are so robust to the virus. So even though you get infected, your immune system will fight against the virus. So just don't panic. If you're so unlucky to get infected, you almost will get recover 100%. Yeah, of course, we don't want this happen. So just stay away from trouble. So don't panic, don't fear. The virus is not that scary as you imagine. Then for me, Xiangyu and me, so we are we are more volatile to the virus since of our age. So we are so vulnerable to the virus. So we need to be more cautious than you guys. So yeah, don't worry about that. We still have our government, and they're going to fight to back us up. Then okay. Okay, another important thing I like to remind you. So you need to wear the mask. The mask need to be changed from day to day. And also when you go out, you return home, you need to wash your hand to clean your hand by the 75% of the liquid. You go to the drugstore. Yeah, I'm not quite sure. You don't have this diluted alcohol, so. Or I hope you can wash your hand by soap. This is no problem. And so this is the two fundamentally important thing you need to do. All right. So admissible control loss, and this XT is admissible if it is a function of this one is a function of the input variable. No, the output variable function of the input variable. XT is the function of the previous XT. So the causal relationship between the X and f of X can be represented as like ST, the next, the control mechanism could be the function form of the YT and the XT. So the problem is we like to find an admissible control law such that the variance of the control output is minimum. So try to minimize the variance of the YT. The variance of the YT is to be minimized. So this is the purpose. Minimum variance is we look at the node dynamics. If this is true, suppose a process given by that, then there's a no system dynamic. There's no autocorrelation. There's only the process gain. This is steady state node dynamic. Then the minimum variance control have it got to be greater than. So take expected value of the y equal expected value of this. So minimum variance the minimum variance to be achieved got to be the variance of the epsilon. So variance of the YT got to be greater than or equal to sigma epsilon squared. So minimum variance control obtained by equating the expected value of the Y equal to the target. Since the variance has been determined, we cannot do anything about that. So you need to only focus on the deviation from target. So there's a two things, deviation from. This is the output variances. Okay, there's the two objectives we like to achieve. So so take the expected value 1. This is the L step ahead. So standing on the time t, we projecting the L period ahead. This is L period at forecast. The L period ahead forecast is expected equal to BT, BX equal to T. So how can we just set out the X, set point the output, then the X equal to the T over B. So T over B, the target over the process gain, the B is the process gain. Pei Zhen, how can we estimate the process gain? Hello.
我在。
Say something. How can we estimate the process? How? By what method?
Regression?
Yeah, cool, very cool. Yeah, regression, correct, very cool. Since, however, regression is offline, so we need to collect the data first. Cool. Collect the data and fit the data by regression. We fit the data regression, then we get the B estimated. Cool. Or regression, or by using the design of experiment and analysis. Yeah, it could be done. Ah, cool. So it's a minimum variance control. Why? Because it is a closed loop from the control policy, closed loop. John, like to compare what is the closed loop versus open loop. John, where are you? At home or in? Okay, in lab. Okay, so say something. Comparison between closed loop and open loop. Yeah, I can speak Chinese. Don't worry. Hello, say something. Hello? At least you need to say something.
Close loop.
什么是 closed loop？ 什么是 open loop？
是那个 SPC。
你说 closed loop 是 SPC， and then what is open loop？ Hello, John. Hello. I don't know. John, are you there? don't know. John, hello. Maybe the instability of the Wi-Fi. I don't know. Hey, Zen. Hey. Yeah, John. So SPC, what is SPC? John?
老师，
是 SPC 是什么？
SPC 是
Statistical process control. Then okay. 上好。And what is a closed loop?
Hi. Closed loop. Have feedback.
Okay, cool. This is a feedback control. Cool. It's a feedback control. So it's totally different. Totally different. So you need to review the material I have taught in class. Okay. Yeah. So the variance of the YT bx plus epsilon. So x is target divided by b. Just plug in here. So the variance, the bb cancel out. The t plus epsilon t is a constant. So variance of the constant plus the random variable equal to the variance of the random variable. So variance of the epsilon t, variance of the epsilon is the sigma epsilon t. So which is minimum achieved by we set x equal to t over b. So yeah, that's cool. So above is the major reason the control policy is used. So this is the minimum variance controller. Okay. So example number 2. So we have example number 1 right here. Example number 2. Yeah, this is a feedback controller example 5.1. We'll look at this. This is a B over 1. So yeah, look at that. This is the target minus mu over B. Mu is right here. This is right here. Okay, so this is let me say that the target. Okay, so the t minus mu over b, if it is an intercept, use a mean quality characteristic if we do not adjust. So qt is a quality characteristic, mu is a mean. So our objective or our interest is to minimize the mean square error of the quality characteristic by manipulating the xt. How can we manipulate xt to achieve the minimum variance control? So minimum MSE mean square error control law is obtained by setting the expected value of the qt equal to the target. So implies that adjustment, the delta t always equal to 0. So now we don't do any adjustment. So delta xt always equal to 0. So if initial is not equal to that, only one adjustment is needed. Right here is needed. So once why the mu equal to target, no adjustment is required. So this is according to the Deming final experiment. Have you remember, if the process is always on target, the process stable, the rule 1 will be the best policy. That's why the no adjustment is needed, since due to the damming, the funnel experiment. Okay, so only the funnel was original off target is a single. If it is not, if X is not set up originally toward the target, only one adjustment, only single adjustment is required, is necessary to end the funnel on the target, after which no further adjustment are necessary. So okay, so the figure 5.4 show the minimum variance law, which is a feed forward, not feedback. This is a 5.4, a feed forward. Hold on. Okay, feedback, that means we're going backward, feed we're going to going forward. So look at that. Hold on. Then we'd like to see the textbook. Okay. Figure feed forward, not feedback controller. That is the value of the quality characteristic are not used in computation of the level of the controller factor. So the objective, no, the value, quality characteristic actually is not used to compute the XT. Let me say it again. This is very important. The value of the quality characteristic are not used in computation of the level. So in here, so let me see that this is a mean, this is a B, so this is a feed forward, a QT. In this case, so the QT is not used in the computation of the XT like this. Then we have a target. We have a minus mu. Mu is the mean. Okay, then how can we get the mean? How can we get the mean? 佩珍 mu. How can we estimate that? Say something. Don't worry. Just speak up loudly. 大胆的说啦，没关系啦。Estimate it. So we take an average. We take the grand average. We take the grand average, then we have estimate mu, right? So then the B is based upon the suggestion by Pei Zhen. She said would like to estimate B by regression. Then so those information not related to the Q. Nothing is related to Q. So that is a feed forward. Not in the feedback. Controller the value of quality characteristic are not used in the computational level of that. Instead, the change in the set point or target are used by the controller. So instead, we use the target. We use a target to as a set point for the controller. So we forward the information to the controller. So T minus mu divided by B and producing XT. XT feedback to the process. The in here B. So we have a XT, right? and the B is a backward operator right here, okay? Then with xt, so xt minus 1 times b again, xt times b's again, and times b's again. Then plus epsilon t to generate qt, as xt to generate qt. Let me say it again. Since xt minus mu divided by b, t minus mu divided by b to produce the xt. Plugging back to here, since this is a deadbeat controller. This is deadbeat. Since that's a deadbeat control, there's a one leg behind. That's why we need to put the backward operator. So we have a t at backward operator t minus 1, then multiply b, and multiply b is this part, then we plus epsilon t into that to produce epsilon t to produce a qt. Yeah, I think that's a kind of, yeah, it's kind of cool, right? Okay, and going back again. Yeah, okay, so this is a FIFO controller. Then, okay, then we move to the next example. 5.2. This is a process with simple dynamics. The dynamics, that means, look at this. We have a dynamic right here, right? Xt minus 1. And the second instant, we have a system system dynamic right here. Since that's a deadbeat for sure, and then we have a system dynamic in terms of the autoregressive term. Autoregressive term. This is AR. This is a P, ARP. So example 2, simple system with dynamics. The process to be considered, to be controlled is like this. Yt plus A yt minus 1. Backward B yt minus 1 plus the C epsilon t. So look at this. No, Jun. What is the component on the left-hand side, Jun? Hello, are you there?
Yes.
Okay.
Yeah.
What is the left-hand side?
Yt.
Yt plus AT t minus 1. My mouse indicating.
AR.
Do you see my mouse moving?
Yeah.
Okay.
Yeah.
What is the part my mouse indicating? This?
AR, I think.
Cool, that's cool, AR. And John, BXT minus 1. John? BXT minus 1. What is the part my mouse indicating? Okay, this is transfer function. And Yu, the last one, do you see my mouse indicating? Yu, are you there?
Yes.
So what is the part? C epsilon t minus 1 plus epsilon t. Hello, Yu, are you there? At least as you need to say something.
Yeah.
This is MA, right? Moving average. Okay, this is moving average. Okay. Then, okay. Where? So where epsilon t is the sequence NN01 IID. Okay, then somehow, what is the IID stand for? This. What does IID stand for?
identical individual distribution, right?
Okay, very close. Not exactly. Not that right. This is an independent and identically distributed. That's called ID. Independent and identically distributed. Yeah, close. Really close. Then, okay. So it assumes the C is less than 1. Okay, so Pei Zhen, why do we have a C less than 1.0? C. Hello? Why we need have C less than 1.0? Why? What? What did it say? 大声一点了。Now, due to that, since we need an invertible. Invertible, okay, invertible. So I tell you need to read the book after class. You cannot always listen to my lecturing only. You need to read the book. Read the book. Okay, then YT stands for the deviation from set point. YT equal to the ZT minus this deviation from the set point. Yeah, the something. Set point is a target. Okay. So then going further, at time t, we need to decide on a control action, xt relating to the process. This is equation 3. Based upon this one of equation 3. Okay, we just plus 1. YT plus 1A, YT equal to the BT, BXT plus a C epsilon T plus a epsilon T plus 1. It's known as the equation number 3. Then move this part, A T minus 1 to the right-hand side. So we would like to take one step ahead. This is the next future observation, YT plus 1, right? YT plus 1. Is the future observation. So it doesn't happen yet. It doesn't. So this future observation depends on the xt. This depends on xt. So we want to select xt such that which minimizes the variance of the future observation. So, which can be the variance of the YT plus 1 equal to the expected value. Since the YT plus 1, let me recap. YT plus 1 is a random variable, right? Based upon the theorem of the variance of the x equal to the expected value of the x squared. No, x is I'm sorry. S squared minus expected value of x. I'm sorry. Expected value of x right? You understand what I'm talking about? You understand that? Okay, the variance equal to the expected value of f squared minus expected value of x squared, right? Then, likewise, in the same manner, so variance of the y equal to the expected value of the y squared minus expected value of the y squared. So this is a quite basic theorem. Then since the yt, I'm sorry, I need to move forward. Okay. Since the yt denote the deviation from target, so yeah, yt deviation from target. So expected value of this one is equal to 0. Yt deviation on target, so deviation from mean, so this is 0. From target, so expected value yt plus 1 is 0. Consistency of the process output on target. Therefore, it suffices to minimize the expected value of the yt plus 1 squared. So in order to minimize this, since this is equal to 0, minimize variance of the yt plus 1, that is equal to minimize the expected value of the y squared only the first time. So from 3, equation number 3. Okay, sorry. Something just going off. So expected, so this one got to be greater than or equal to expected value of epsilon t plus 1 squared. Why? Like this. Like this. This is I'm sorry. Expected yt plus 1. Yt plus 1 is like this. This one. This one. Expected, this is squares, this is things out. So from 3, this is the best we can do. This is the best we can do, right? This is the best we can do. So that is 1.0. We assume the standard deviation of the future error is 1.0. The best control X will make the variance of the output greater than or equal to the sigma epsilon 1.0. So look at the number 3. Since this is a future error, actually we can do nothing about that. And for the C, so this is the residual. So it's a constant. So it is not contribute any variability to the variance. So from 3, so minimum mean square error forecast for the yt plus 1, that is a minimum mean square error forecast. So given t and the 1 step ahead forecast, this 1 step ahead. This is a 1 step ahead forecast. If we can let this, based upon 3, based upon number 3, equal to that. Okay. Move to that. This minus AT. Take the expected value. This is a constant. So expected value of epsilon t. The future error, we cannot do anything about that. That is equal to 0. So if we can do that based upon this, then they're going to be the minimum mean square error forecast. That is in the chapter 3, MMSE. This is MMSE described in chapter 3. Chapter 3. Okay. Chapter 3. So, Okay, so this is one step ahead forecast. What is going to happen next? Let me see. So suppose that we choose XT to let the one step ahead forecast, since this is a deviation from set point, deviation from target. We let this equal to 0. We let this equal to 0, then we can solve XT. What is going to happen? This is equation number 4. So we let this equal to 0, then we have equation number 4, XT. XT equal to the AYT minus C epsilon T divided by B. This is AYT minus C epsilon T divided by B. Bingo. So that is a minimum variance controller for equation number 3. This is sorry, minimum variance controller for equation number 3. Okay, then back to the slide. Then we'd like to confirm how can it be true. We substitute the 4 back to the number 3. We just stuck in here, plug in here. What's going to happen? Well, very cool. YT minus AT, this is number 3 right here. Move this to the YT plus 1 minus A minus AYT plus a B and plug in XT. Yeah, plug in XT, AYT minus C epsilon T, B, boom, boom. Going to cancel out. That's so cool. That is absolutely so cool. They're going to cancel out this. Going to cancel out this. The only thing left is future arrow. Yeah, this is the coolest thing I ever seen. Since the only left is a future arrow, that means we cannot do nothing about that. So just let it be alone. See that? The all cancel out, so the future observation last only subject to the future arrow. So which definitely valid for all time periods. That is to say, expected value YT plus 1 equal to this one, like this. So expected value of the y squared equal to the variance of epsilon T plus 1, 1.0. Minimum we achieve. So cool. That is to say, equation number 4 is the minimum variance controller. Yeah, this is the coolest thing I ever seen today. Okay, I stop here. Then, okay, there is call it a day, and I stop here. It is a very important chapter, chapter 5 and chapter 6. That is important for the final project. So I'm going to have a class today, right here. I stop here. Any question? No. 项羽 do you have any question? 项羽。
这个对我来讲有点难度了，所以我需要再研究一下。
Okay. Jin, any question?
No.
No, you need to read the book. 上好 any question?
No.
You got a lot of questions. 佩珍 a question?
没有。
Hello.
目前没有。
Okay, John, any question?
No.
No. Yu, any question?
No.
Not yet, right? You have a lot of questions. However, you don't know how to ask.
Yes.
Okay, go away. Any question?
还要再看一下。
Okay, so let's call it a day. Then we're going to have a test. So we're going to have a test next week. open notes and open book. So you need to turn on your video. Let me see you. Let me see you. So I will send the Word file to Line Group. You just download it. You can print it out. Use a pencil to fill your answer. Or you can just download the Word, directly type your answer into the Word file. Do you understand? Do you understand?
Yes.
Okay, then you're going to return. Then when you finish your answer, you need to transform into the PDF and send it back to me by email. My email going to be like this. So you need to send it back by 11:10 by email. I will see the timestamp. 所以你们一定要在11:10就把它寄出来。I will see the timestamp. Do you understand?
Okay.
Okay. 只有2个小时。So I only allowed you 2 hours to finish your midterm exam. So you need to send it back by only PDF. Okay, I think that is good enough for today. I hope you're doing fine. Stay home, stay healthy, stay away from trouble. Okay, I see you next week. 佩珍，
哎，有在。
录完影再传给我啊。好，
好。
好，拜拜。